Exercise 1614 says the H1 NMR spectrum, or the proton NMR spectrum, of a compound with a molecular formula of C7H15Cl exhibits two signals with a relative integration of 2 to 3. Propose a structure for the compound. Now, the relative integration, those are the number of hydrogens in the relative number of hydrogens in each signal. Now remember, each signal is representing an electronic environment, so that means you would have 2 hydrogens in one electronic environment for every 3 hydrogens in another electronic environment. That ratio of 2 to 3 should really remind you of an ethyl group. You'd have, here's your 2 in one electronic environment and 3 in another. So really, that ratio should remind you of an ethyl group. But let's say you didn't notice that. You said, okay, 2 to 3, I guess. What now? There's a big principle that's being illustrated by this exercise. And it's that if you ever have a lot of hydrogens and only few signals, you have symmetry. So a lot of hydrogens, normally if there's no symmetry, that would mean each one of them would be in different electronic environments, and so you get a whole bunch of signals. But if you have a lot of hydrogens and few signals, it should be like flashing lights, symmetry. That's the only way that you could have a lot of hydrogens in very few electronic environments. So, well, we know that there must be some sort of symmetry there. That's the hint. And so let's just start by drawing the simplest 7-carbon chain we can find. So here's 1, 2, 3, 4, 5, 6, 7. Now we know there has to be symmetry, so the only way you can get symmetry out of this 7-carbon chain is to make symmetry and make a vertical line down the center. Now we have this one weird atom, the chlorine, and in order to keep the symmetry, the chlorine would have to be coming off of that middle carbon. But notice the number of different electronic environments you'd have here. You would have the hydrogens on that CH2, close to the chlorine, that's one electronic environment. You would have the hydrogens on the next CH2, a little further from the chlorine, that's a second electronic environment. And then you'd have the hydrogens on the CH3s, the methyl groups, even further from the chlorine, so that's a third electronic environment. This would give rise to 1, 2, 3 signals. But they told us in the problem that the true molecule only has 2 signals. So this can't be the true molecule. Okay, so how can we modify this? We have to keep the symmetry. What if we took away one of the hydrogens, one of the carbons. So we took this away. Well, you can't do it to just one side, because then you don't have the symmetry anymore. And we know we have to have symmetry because we have a lot of hydrogens and very few signals. So if you take a carbon away from one side, you have to take the carbon away from the other side. Okay. Well, now we have to add those 2 carbons back in somehow while preserving the symmetry. And you can add them in 2 different ways. So let's add them in those 2 different ways and see how it would affect the molecule we get. We can't add them on the ends, then we end up with what we had before, and we saw that that gave us 3 signals. If we could add them on the next carbon in, and let's see if that gives us the 2 signals that we want. Well, here, there's a hydrogen on that same carbon as the chlorine, so that's a 1 electronic environment. That'll be 1 signal. Then, you'd have hydrogens on that carbon with the branch. And finally, you'd have hydrogens, these all would be the same signal because of the symmetry. So, you'd have these should be a different color, sorry. So these are all in the same electronic environment. So you'd have 1, 2, and 3 So 3 signals here, but we know we should only have 2. And so that can't be the correct molecule. Okay, well, we still have to add those 2 carbons in. We said we couldn't add them on the end because that would be the molecule we started with. It has 3 signals. We can't add them to the next carbon because, again, that gives us 3 signals we just saw. We can't add both of them to the carbon in the middle because now that carbon would have 5 bonds. It doesn't have enough room for all of those electrons. That would be 10 electrons. It only has an s orbital and 3 p orbitals. So that's 2 plus 2 plus 2 plus 2, that's 8. So it only has room for 8 electrons around it. So you can't put the 2 carbons as separate methyl groups attached there. What you can do is have one come off and the other come off of that. And now notice you have the ethyl groups that we talked about at the very beginning, 3 of them. You have hydrogens, you have no hydrogens on the carbon that's attached to the chlorine. That carbon has 4 bonds to other stuff, no hydrogens there. You have 2 hydrogens that are all next door to the carbon that has the chlorine. That would be 1 electronic environment. That's 1 signal. Then you have hydrogens that are on the CH3s, 2 carbons away from the carbon with the chlorine. That's a 2nd electronic environment. So here there are only 2 electronic environments and so only 2 signals. And notice the ratio of the hydrogens to each other. Here there's 2 hydrogens plus another 2 plus another 2. That's 6 hydrogens in that first electronic environment. On the end you'd have 3 plus another 3 plus another 3. That's 9 hydrogens in our second electronic environment. And so you can simplify that. A ratio of 6 to 9 is the same as 2 to 3. If you divide both of these by 3, you get 2 to 3. So you can see that we have those 2 electronic environments and the ratio of hydrogens in them is 2 to 3. So in this one, there are two principles you really want to take away from this. The first principle is that, and the main one, is that whenever you have a lot of hydrogens and few signals, you must have symmetry. And aside from that, the one recommendation I'd have for you is that when you're trying to figure out a structure, don't just randomly try structures. Start with a standard structure like we drew out the 7 here, and then systematically change it. Change it in a way that follows a pattern and is systematic. We took off the hydrogens at the end, the carbons at the end, for example, and then we put them on the next carbon inside. When that didn't work, we put them on the next carbon toward the center. But just keep in mind this one pattern that you can, if you have a lot of hydrogens and a few signals, then the molecule you're trying to draw has symmetry.